Hi there, U10. This is your worked answers to the booklet pages 7, 8, and 9. Hopefully you've had a go at these yourself first, and you're now just checking your work. Feel free to fast forward through the video and just look and put ticks in your booklet where you get things right and fix them where you get them wrong. I will be walking you through and explaining. So if you want to watch the whole video, you can get the explanation. Right, so states of matter and particle diagrams. For these, you needed to look up the elements on the periodic table. You do not ever have to memorize element symbols. So C is carbon. This is an element because every atom is the same. They're all carbon. They are giant because it's one continuous network. And this is a solid because they're in nice, neat rows. Second one has two different elements. It has C, carbon again, and H, which is hydrogen. Because the C and the H are touching in this diagram, they're bonded, this is a compound. They're in units. Each unit has a C in the middle and 4 H's around it, so it's a small group of atoms. That's the definition of a molecule. And then solid, liquid, gas for this one is a little tricky, but if you look at the circles I've drawn, these are 3 separate molecules. They're not touching. They're not in neat rows. This is a gas. Now, the way this is drawn, they are awfully close. You could say it's a really warm liquid that's kind of just becoming a gas. Kind of see where you're going, but really, liquid particles would be touching. These are not. There's a definite space between them, so I would classify that as a gas. The next one, again, this one confuses students because they think of this as giant, but it's actually not. That's an O with 2 H's, and there's another one, and there's another one, and another one. So what you can see here is these are actually molecules that are just touching. And I've circled all the individual molecules. So we've got H and O, hydrogen and oxygen. They're definitely bonded, so compound. It's individual molecules. It's water, right? Water is H2O. And this would be liquid water. If it was solid ice, they'd be in neater arrangement. If it was a gas, they'd be spread out. So this is a liquid. Almost done, 3 to go. This one has Na and Cl. Please be careful with symbols. When there are 2 letters, the second one has to be lowercase. So capital N, lowercase a. And these are sodium and chlorine. They're bonded, so it's a compound. This is giant, and it's a solid. It's exactly like the one that was carbon at the top of the page. Nice, neat rows, all connected. Ah, finally, we got our first one where they're not bonded. We have got H's and O's separate from each other. So that means this time it's hydrogen and oxygen, but rather than being a compound, it is a mixture. This is what we mean when we say mixture. 2 different substances in the same container, but not bonded. These are both molecules, and they're a gas because they're not touching, and they're spread out. Last but not least, we have capital N, lowercase e, that is neon, the noble gas. It's an element, they're all the same, they're individual atoms, and these ones are a gas. And there you have it, that's page 7. If you did the extension, you should have drawn, for the first one, some H2 molecules. That means 2 hydrogen atoms connected, and single argon atoms. And you'll notice my hydrogen molecules and my argon atoms are not touching because it's a mixture. Steam should look very similar to your water picture, except instead of being all right next to each other, put the water molecules spread out. I love water molecules. They look like little Mickey Mouses. O with 2 little H's. All right, moving right along, page 8. For this one, you really should have watched the video. Please, please watch the video. Don't just copy my answers down because the video goes into all the visuals and shows you the experiments. It's much, much more exciting than listening to me talk. What does diffusion mean? Right, in chemistry, GCSE, you are not asked to give a long-winded definition for diffusion. All you have to know is that it's particles spreading out. Okay, they will fill their container. So if you have a bit of perfume and you open the lid of the bottle, the particles will slowly spread out to fill the room, and eventually you'll smell that lovely perfume. Anytime you smell something, it's because the particles diffused away from the source to your nose. It only works if particles are a liquid or a gas, because they have to be able to move. Solids can't really diffuse because they're stuck in place. Okay, choose the correct diagram. So they had bromine, this dark reddish brown gas, and air, colorless gas. So diffusion means the air particles spread to fill the container by moving down, the bromine spread by moving up until they're all mixed. So our correct answer is R. Not P, because you don't get double the bromine. They've mixed, so you'll end up with a 50% bromine and air in both sections. Why does it take so long? It's because the particles collide with each other. They don't just go on a smooth track up or down. Okay? You've got air, and you've got bromine, and they're going all over the place, colliding with the walls of the container, colliding with each other, and slowly but surely they make their way to spread out and fill the space. Nitrogen dioxide diffuses a lot more quickly than bromine, and that's simply because it's lighter. NO2 is nitrogen dioxide, and it has much less mass than Br2. Lighter particles move faster. Okay, the example I always give is, imagine I tried to kick a soccer ball and I tried to kick a bowling ball. Okay? If I put the same energy into kicking a soccer ball, it might fly across the field. The bowling ball would hardly move, and I'd probably hurt my foot. Okay? It takes a lot more energy to move fast, to move heavy things. So the bromine is heavy like a bowling ball, just bumbling along. The NO2 is whizzing along because it's so much lighter. If you want to check how much lighter, you can actually look it up. You just need your periodic table. Bromine, each bromine is 80 AMU, so that would be 160. And if you look up nitrogen on the periodic table, it's 14 is its mass. Oxygen, relative atomic mass of 16. So we're looking at 32 plus 14 for this one, which gives you 46. 46 is a lot lighter than 160, so that will move much faster. Okay, the last experiment on the video was this really classic one where you have a long tube and you put HCl on one side and NH3 on the other side, and they react, and you get a white cloud, and the white cloud is way over here, closer to the HCl. The name of the cloud is ammonium chloride. You do have to memorize that. Ammonium chloride is simply the product that forms when these two gases react. You take NH3, you react it with HCl, and you get NH4Cl. Why are they labeled as G gases when in the video they showed them as solutions? Well, it's because it's much easier to put them into the container as solutions. By the time they react, however, they have evaporated. The NH3 and HCl evaporate first, then react as gases. So the idea here, guys, is to do the experiment, you start with a solution. But by the time they've reacted here in the middle of the tube, they had turned into gas particles and had whizzed their way or diffused their way through the tube. Which traveled faster? This is the whole point of this experiment. Which diffused faster? Well, if the white cloud formed closer to the HCl, it means the HCl didn't move as far because it was slower. So the NH3 is faster. Because its particles traveled farther. Why? Because it's lighter. This is because NH3 is lighter than HCl. So this video went through what diffusion is and the fact that lighter particles diffuse faster. Page 9. Diffusion in liquids. Oh, I love this lab. I'm so sad you didn't get to do this in person. So you take the Petri dish. Hopefully you saw. I think they had pretty good video quality there. He added solid lead nitrate and solid potassium iodide on either side of a Petri dish. So that would be the potassium iodide, and that would be the lead nitrate. And they were solid. So first they had to dissolve. And then once they dissolved, they like creep their way, or diffuse, through the water. And you get this lovely, sparkly yellow, solid product. Okay. It's so cool because you put them over here, they travel and meet in the middle and they react, and I love it because lead iodide is just a beautiful substance. Very toxic, very dangerous, but it's a shiny yellow crystal. So what evidence was there that they were moving? Well, it's simply that they reacted in a different spot to where they started. Okay? The product formed in the middle. So the reactants must have moved. Okay? Must have moved through the water and made their way to the middle of the Petri dish. Okay? Part 2 is the one you can either do yourself at home if you're feeling adventurous, you want to get out the water, you want to get out the food coloring and do it yourself. Awesome. You can also watch me do it. I made a very low quality iMovie. Don't judge me. So feel free to watch that. You then need to answer these questions, so both the results and the 3 conclusion questions. That is an assignment on Saltus Live, so once you've answered them, upload that and I will grade it for you. As always, any questions, send me an email. See you later.